Hello everyone. In this video, I will go over my solution for the problem named three-sum closure taken from today's Codeforces round. This problem is an excellent problem which teaches you how you can use greedy ideas with basic math inequalities and how you can use casework in order to reduce this problem to a brute force problem which can be easily done efficiently. So in this problem, we are basically given an array A of length n. The array A is called three-sum closed if for all indices I, j, k such that I is less than j is less than k and these three indices are between 1 and n, the number ai plus aj plus ak is contained in the array. So there is at least one element in the array which has the value ai plus aj plus ak for every triplet of integers I, j, k, and we need to print yes whether this holds true for all possible triplets I, j, k and no otherwise. So first of all, before we even look at the constraints, it's clear that an O of n cube solution would be to iterate through all triplets and check with O of 1 using a map whether ai plus aj plus ak is present in the array. So this is actually O of n cube log n because map takes log n time to access the elements and the elements can be up to 10 power of 9. So it's clear that a very simple implementation of this would be to just iterate through all pairs or all triplets and find out whether the condition is met or not. So if the condition is not met for any one triplet, we'll print no, because this should hold true for all integers I, j, k, where 1 is less than or equal to I, is less than j, is less than k, less than or equal to n. So that's the simple brute force logic. Now let's try to reduce the original problem to a brute force logic by performing some casework and some math. So before that, let's look at the examples. In the first example, there are only three elements. So -1 plus 0 plus 1 will give you 0 and 0 is contained in the array. So we will print yes because the value of L can be anything. So L can be equal to I, it can be equal to J, it can be equal to K. The only condition is that L should be that the number AL should be there somewhere in the array. It does not matter what index the number occurs. So in this case, it's clear that even though we choose the indices as 1, 2, 3, the value of L is also equal to 2. So it's fine that there's an overlap. I is 1, J is 2, and K is 3, and L is 2. So that is allowed. In the second example, where this is the array, if you sort the array, you can see -2, -2, -3, 1, 1. So the first thing to do always in such kind of three-sum problems or like any kind of problem where you are given the sum of three elements in the array and you want to equate that to something else. Our first key step is to always sort the array. So let's look at the sorted array. The sorted array is this -3, -2, -2, and then some other elements 1, 1. So the moment you sort the array, one thing becomes very clear that if you take the sum of the smallest elements, then it's clear that the sum of the smallest elements is smaller than all the other elements. So in this case, the sum is -7, which is less than all the elements of the array. And that's why it's clear that the answer is going to be no, because we know that these three elements have a sum of -7. So this is one triplet which contradicts the three-sum closed property. So we'll just print no directly. So that's one observation which you can make. If you just add up all the smallest elements and if that sum is less than -3, then this automatically gives you a no, and you can just print no straight away. Now let's go to the next example and see if we can make any observation. So in the second example, the array consists of all zeros. So that's why when you add any three zeros, you get back a 0 and 0 exists in the array. So we print yes because it's three-sum closed, like all triplets of zeros will give back 0 and 0 is contained in the array at least once. So we will print yes. In the next example, again, you can consider like the three largest or the three smallest values or some combination of values, and you'll see that I think if you take 4, -1, -3, you get 0 and 0 is not contained in the array. So that's one possible triplet which contradicts this requirement, and that's why we know that A is not three-sum closed, so we print no. In general, the key idea revolves around this fact that we should always take the largest values or take the smallest values. And now let's actually use some formal math in order to make a concrete observation. So the first observation is that if you take at least three positive elements, so if the array contains at least three positive elements, then we know that uh, since there are at least three positive elements, then we can just take those three positive elements to be the last three elements. Let's call them, let these elements be a of n minus 2, a of n minus 1, and a of n. So let these three be the elements. Then clearly a of n minus 2 plus a of n minus 1 plus a of n is greater than all the elements. So I'm considered A to be the sorted version of this array. So I've sorted A and I've done this thing. So clearly, since all these elements are positive, that's why this inequality holds true, and that's why uh, therefore an minus 2 plus an minus 1 plus an does not appear in the array, and we can directly print no value. So we can directly print that the answer is no, because if you consider the largest three elements, if you add them together, that sum will not appear in the array. And this is the key observation which I was talking about. The same thing holds true when you consider three negative elements. So three positive elements or three negative elements. The same logic holds true for three negative elements. And in that case, obviously, we will not take the three largest elements, we'll take the three smallest elements. So what we will essentially do is we'll sort the array and consider the three smallest elements. So we know that since there are at least three negative elements, the first three elements like a1, a2 and a3 should all be negative. And since they are all negative, elements, we know that the sum will definitely be less than a1 because they are all negative. You can verify this with examples if you don't understand it fully, but like this is the key observation, and therefore in this case a1 plus a2 plus a3 does not appear in the array. So this means that for both the cases when there are at least three positive elements or there are at least three negative elements in the array, we know that the answer will be no, because we have found a triplet which does not satisfy this property. So the moment we have found a triplet which does not satisfy this property, we print no. That's what the problem is essentially asking us to do if you read it carefully. So that's what uh, basically helps us reduce the problem a lot, because now what we essentially need to do is we can ignore the cases when the array has three positive or three negative elements, and what we essentially need to do is we need to consider the case when there are a lot of zeros. If we eliminate the case when there are a lot of zeros, then we are essentially left with an array of size at most 3 or at most 2. I mean, like, there can be at most 2 positive elements, 2 negative elements. So there can be at most 4 non-zero elements. So if you eliminate case 1 and case 2, let's go to case 3. So case 3, the array contains at most 2 positive and at most 2 negative elements. So this means that we can just do a brute force over all the positive and all the negative elements and just iterate through all triplets. So there can be at most 4 numbers which are positive or negative. However, the problem appears when there are zeros. So in order to solve the case when there are zeros, we can again do casework. So case 1 we print no, case 2 we print no. Now we have entered case 3. Inside case 3, we need to think about what are the cases for the number of zeros. So let's say count of 0 represents the number of zeros. So if count of 0 is 0, so that's a simple case. We just like iterate through all triplets. So iterate through all triplets, uh, and there can be at most 4 choose 3, because uh, there can be at most 4 choose 3 iterations, because the length of the array is at most 4, because we know that the array contains only 2 positive and only 2 negative elements. So that's why the term complexity is like 4 choose 3, which is approximately like 4. So it's very, very small. So when count of 0 is 0, it's very simple. Otherwise, if count of 0 is 1, then we need to check whether, first of all, we can obviously iterate through all triplets. So iterate through all. Again, we can iterate through all triplets, but another way to look at this is we iterate through all non-zero triplets. So we look at all the positive elements and all the negative elements and iterate through them. So this takes 4 choose 3 iterations. Then we also consider the 0, then iterate through all and all then iterate through all 4 choose 2 pairs and add a 0 to the sum, and add a 0, because exactly 1 0 appears. And that's why, like, you should you can either brute force it, or you can just iterate through all pairs and add a 0 as well, because exactly 1 0 appears in the array. Now for the final case, when there are three zeros or more, uh, so let's consider when there are the next case, when there are two zeros. So if there are two zeros, then there's actually not a separate case. So this one should actually be for all count 0 greater than or equal to 1, and I'll be explaining right now why uh, this shouldn't matter what count 0 is. So if count 0 is like 2, then obviously if you consider two zeros and add them together, so let's say you're adding two zeros, so 0 plus 0 plus ai, so this is the sum, and that's obviously equal to ai. So this will always hold true for any number of um, index I between 1 to n. You can just consider 0 plus 0 plus ai, and that's equal to ai. So there's no separate case involved for two zeros or three zeros. Even when you have three zeros, 0 plus 0 plus 0 is 0, which appears in the array. So for all the occurrences of 0 greater than 1 or equal to 1, you can do the same thing of first iterating through all non-zero triplets. This will take only 4 choose 3 iterations. So this is your first step. And then your second step is to iterate through all pairs and add a 0, because you should consider adding a 0 to each pairs of sums. And you don't need to consider iterating through each individual element and adding two zeros, because we know that if you iterate through each element and add two zeros, you'll get back the same element. So there's no need to consider that. That won't give you a no. So basically, what we are doing is we are checking for a no in a brute force manner, and we are checking for a no by iterating through all possible triplets or all possible pairs and adding a 0. And that's why this will easily work within the time required, and it will also be correct, because what the problem is essentially asking us to do is to check whether there is at least one triplet such that ai plus aj plus ak uh, is not equal to al for all l in the array. So we are essentially trying to find a triplet such that their sum is not present in the array, and in order to do that, we can use basic casework, as I mentioned. So in total, there are three cases, with the third case having two sub cases. And now I'll just show you the code which implements the same idea. So in the code, first, for each test case, I take in the value of n. I maintain the count of positive elements, the count of negative elements, and I use a map to represent the frequencies of each number, because so that we can check in O of log n whether or not ai plus aj plus ak appears in the array. And what I'm doing is I'm storing all the non-zero elements, so storing all the non-zero elements in the array B, so that we can brute force over B in O of one time. And because B will contain at most two positive and at most two negative elements. So once we do that, once we store all the non-zero elements in B, the brute force takes O of one time, and that's the key logic behind the whole solution. Now, for each value of I going from 1 to n, we take in the value of ai, we increase the frequency of ai by 1. If ai is positive, we increase count positive. If ai is negative, we increase count negative. And if ai is not equal to 0, we just add ai to the vector b, and I just use the normal pushback to add to the vector. Now for the main part of the brute force. So before the brute force, obviously, if count positive is greater than or equal to 3 or count negative is greater than or equal to 3, we can use the greedy idea of choosing the three largest or three smallest elements respectively, to get a sum which is guaranteed to be outside the array, because of the inequality which I just mentioned in the whiteboard. And that's a very simple inequality, that if you add three positive numbers, that the sum of those three positive numbers will be greater than the max of those three numbers. And similarly, the sum of three negative numbers will be less than the min of the three negative numbers. So that's the inequality which I used over here to print no. Otherwise, we know that the array B contains at most three elements, so we can do a brute force. So this is the normal brute force. Iterate through all triplets and check if ai, so in this case we are using b, so bi plus bj plus bk, to check if count of bi plus bj plus bk is equal to 0. If it is, then this means that we print no, because the triplet does not, because the array won't be three-sum closed, because there is at least one triplet such that the count of elements which have the sum equal to the sum of those three numbers in the triplet is 0. So if the count is 0, then that means that if you choose ijk to be the triplet, then the condition won't be met basically. So that's why we print no. So that's iterating through all triplets, where all numbers in the triplet are non-zero. If you want to include zero elements, so include zeros in the triplet. So to include zeros in the triplet, we notice that only one occurrence of zero is required, because if you add two zeros, they will basically give a sum of 0 plus 0 plus b of I, which occurs in b of I, which occurs in the array A, because b of I occurs in the array A. So we don't need to check for the case when there are more than two zeros. We only need to consider one occurrence of a zero, and essentially we can again brute force over all the pairs of elements. So for all pairs of elements, if count bi plus bj is equal to 0 for any pair of elements, we'll set is to be false, and is basically represents whether or not the array is three-sum closed. So that's essentially like the whole logic of this is essentially the full brute force, which is just a clever adaptation of the of what the problem is asking us to do with the inequality observation. So you can verify that this code gets accepted, and you can actually remove uh, some of the predefined code. So in order to make the code shorter, I'll just remove all of this. So you don't need to use fast IO for this problem. In general, it's a good idea to use fast IO, but I don't think it's required in this problem. And I'll just submit this code to see that it gets accepted. So as you can see, my code got accepted. Without fast IO, it takes about 4 times as long as with fast IO. So you should, in general, always use fast IO, but it's not necessarily required. So I hope you like this problem and my solution. If you have any doubts in any part of the solution, do leave them in the comments down below. And if you like this video, don't forget to give it a thumbs up. Thank you.